Hello, everybody. Welcome back to your favorite class. Sorry if you showed up at lecture today. I'm not actually there today, as you can tell. I'm like 700 miles away in Pennsylvania. So I'm here for some personal reasons and won't be in town at all this week. So I'll be doing all my lectures this week virtually. And especially on Thursday, you wouldn't have had in class anyways because you have your first exam on Thursday. So just a reminder for that. A couple of announcements I want to make. Your homework number 4, which is kind of on the first part of anisotropic materials, will be due tomorrow, right at the beginning of lecture, 4 o'clock. And then Wednesday, we're going to have an exam review session at 7 o'clock p.m. So I just sent out an invite for that over Teams. Hopefully you got that. I will record that. I know it's kind of a late minute sort of decision, but I will record that. So if you'd like to watch that or you can't make it at that particular time, you can watch that a little bit later if you want. In that review session, we'll just kind of be going over the study guide that I sort of sent out. So if you're kind of already comfortable with all the stuff that's on that study guide, you might not necessarily need to attend, but I thought it'd be good to kind of do it together as a class. So that's that. And then obviously your first exam's in class on Thursday. There's some instructions on Blackboard for how we're going to do that and how that's going to go. So make sure you take a look at that and sort of digest that before you show up. I'd obviously advise you to come a couple minutes early and make sure everything is in order for that exam. You're ready to go. Okay, so any questions on that? Okay, well, there's no questions. Let's get down to business. Business. So I just want to talk a little bit about where we sort of left off. We were talking about kind of the anisotropic materials and how stiffness matrices are transformed. All right, so last time we were investigating our stiffness matrix. And just so you remember, our stiffness matrix, if we're talking about stress states at a particular point, this is going to be the stiffness matrix we call capital C multiplied by the strain, which is epsilon. And generally, we said that if we're writing in contracted notation, this is a 6 by 1, this is a 6 by 6, and this is a 6 by 1. Okay. The inversion of this, obviously, Hooke's law is the compliance matrix. Here's S. And our stress state sigma, where again, this would be a 6 by 1. Strain state, this is a 6 by 6. The compliance matrix, this is a 6 by 1. So this is Hooke's law that relates stress and strain back and forth. And we were looking at, okay, here's our stiffness matrix C or our compliance matrix S. Generally, they would have 36 entries. With, our general condition of conservation of angular momentum. And it would have 21 entries with our Cauchy elastic assumption, which says that this stiffness matrix Cij is symmetric. All right. And so if we're talking about a stiffness matrix for a material, the 6 by 6 matrix, we would have to populate, all of these constants inside of that stiffness matrix. That would be 21 independent entries to fully define how a material responds under stress or strain accordingly. And, we know from, ME2004 and ME3005, these mechanics courses, that if we're dealing with isotropic materials, you only really need 2 elastic constants to fully describe sort of like the Hooke's law for a material. So if isotropic, then the stiffness matrix C would have only 2 independent entries. Okay. And last lecture, we sort of showed how to go from sort of our general isotropic material to the isotropic material. That was in last lecture. And that was by leveraging our planes of symmetry and isotropy. So remember, our plane of symmetry is one where if we rotated the material 180 degrees through an axis on a plane, you would have the same stiffness matrix C. Or if you had a plane of isotropy, you could rotate about any angle through an axis perpendicular to the plane, and you would have the material properties unchanged. So that's what we discussed last time, and just as a reminder, we did an example of this with a rotation about an axis through plane of symmetry. Or let's say we had a unidirectional composite that looked like this. And we got our fibers running in this direction, generally our one direction. Or here, these are our fibers. And we had a coordinate system that looked like this. And we said that the stiffness in this particular coordinate system, we call it the 1, 2, 3 coordinate system. Since this is a plane of symmetry, would be equal to the stiffness in the 1', 2' coordinate system, where this 1', 2' coordinate system is a coordinate system that's rotated 180 degrees from our original coordinate system. Okay. And this would imply that we sort of have a plane of symmetry, and this is sort of the assumption that we made. Because if you thought about like rotating that guy 180 degrees, it would behave the same in both directions. And so we used our transformations, which was something like here. Let's make sure I get this right. I don't want to say this incorrectly. You could have something like a transformation matrix T multiplied by your stiffness matrix in 1', 2', 3', multiplied by the inverse of the T star matrix, getting you back to your original matrix. And we showed that when we execute this math here, there were some entries in what ends up being this entire matrix that are sort of negatives of the first stiffness matrix C123. And the idea there was that the entries in this sort of newly calculated matrix on the right-hand side, if they are negatives of sort of the stiffness matrix on the left-hand side, then those entries must be 0 by sort of default. Okay, so we did this and we saw, for instance, that entries had to be 0. And so we eliminated 8 variables that we needed to define our material just by understanding that there's one plane of symmetry in this particular problem. So it's a very powerful idea of mathematically enforcing the symmetry by rotating about an axis on a plane and enforcing that the stiffness matrices for the two materials have to be the same. So you can further simplify and eliminate more constants and define the material symmetry along the way, and so on and so forth. And so that's what we kind of did last lecture. And we made our way through all these kind of different definitions of various materials: orthotropic, transversely isotropic, isotropic, etc., depending on the levels of symmetry that we had. And so to summarize, I've put together kind of a nice summary of all this information in one particular slide. And so now I'm looking at slide number 8 of the notes. So in summary, I have something that looks a little bit like this. That tells you your general classification of the material. Here's a general anisotropic material. Monoclinic, we talked about, orthotropic, transversely isotropic, isotropic, etc. All these various definitions that we have for materials. How many planes of symmetry and planes of isotropy they have, and then how many independent constants of Cij and Sij are required to sort of fully define those particular stiffness or compliance matrices. Okay, and some examples here on the right. So this information here, which is slide 8 of lecture number 6, this is the last piece of information I would expect you to know for the exam coming up this Thursday. So everything up to this point is fair game for the exam. And this chart you should know because there's probably going to be a question, at least a theoretical question about stuff that's in this chart. So got to know it, got to sort of understand how this rolls. One last thing that I want to mention is that the classification of the material is, you could think of them as like necessary and sufficient conditions to be defined as previous. Okay, so what I mean by that is if I was considering what is a general anisotropic material? Okay, excuse me just a second. Can you please take the dog? Okay. All right, sorry, I got my dog bugging me here. So if we had to classify these particular materials and we thought about categorizing them in a sort of a stochastic way, you might have the largest group being like this general anisotropic material. So I'll call it GA, all right? Then within that particular bubble, all monoclinic materials are generally anisotropic. Okay, so you could think of like another bubble inside this. This is like the Russian, bubble doll or whatever, where this is here as monoclinic. All right, so all monoclinic materials are generally anisotropic, but not all generally anisotropic materials are monoclinic. Hopefully we can understand that by the picture. And we can go down further and further with our Russian doll. This is orthotropic. Inside of that, we have transversely isotropic, and then finally, in the smallest bubble, isotropic material. So isotropic materials would generally be considered as general anisotropic materials, which is a little bit strange to understand, but the classification scheme sort of like works its way down in that way. Someone making a comment. It's called Matryoshka. Okay, that's the serious name that Cuddy has for the Russian dolls. Did I pronounce that right? Okay, so that's the general idea there. So for example, a material that is orthotropic is also monoclinic. But a monoclinic is not necessarily orthotropic. Got me? Okay, so let's continue on now. And I was kind of alluding at the last lecture that we had on Thursday of, yes, it's nice that we can sort of like reduce these stiffness and compliance matrices down to two independent entries, but it would be much more convenient if we could actually write them in terms of engineering constants that we know, like the elastic modulus E, the Poisson's ratio nu, shear modulus G, so on and so forth. And that's what we're going to discuss today is, yeah, we can whittle them down using these sweet math tricks, but how do we get them from like C11, C12 to things like the Lemay parameter lambda or the stiffness E, etc. Okay. So let's make that point here directly. We'll call this section incorporating your engineering constants. So for example, we have the stiffness matrix like Cij, or the compliance matrix like S. Oh, jeez. And this Sij with entries of for instance, like C11, C12, blah, 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 or S11, S12, blah, blah, blah. But that's not really helpful. We want in terms of like E1, E2, G12, nu12, etc. These like engineering constants that we've come to like know and love. Okay, so how can we write Cij and Sij in terms of those engineering constants? In terms of those guys, that is the question that we're going to tackle today. Okay, the first thing we're going to do is we're going to start with an orthotropic material. That's because this is kind of like the most generic composite that there is, would generally be classified as orthotropic. All right, so let's start with an orthotropic material. And specifically, I'm going to start with the compliance matrix, and the reason why I do that will sort of make sense as we go on. So here we'll start with compliance matrix. Of an orthotropic material. Okay, so the compliance matrix of an orthotropic material, if we just sort of remind ourselves, this would be like Sij, which is a 6 by 6. But an orthotropic material, we need 13 parameters to define. And if we want to write this compliance matrix in like Hooke's law, you'd write it in contracted notation as like epsilon equals S times sigma. Or if you wanted to write it in expanded form, you don't necessarily have to copy this down, but just understand that if we have an orthotropic material, that contracted form could be expanded to look something like this. And remember here that this is specifically for an orthotropic. So we have a lot of these zeros that have popped in here because we've sort of already done those rotations about the planes of symmetry that exist in this material to sort of pop those zeros into place. Same thing with like all these other guys over here. All those zeros are popping in because we've sort of reduced the compliance matrix S according to the sort of rotations about the plane of symmetry that we've talked about before. Okay, so here we are, and this is generally what we're going to start with, this sort of orthotropic material definition. And what we're going to do now is we're going to perform like a mock experiment where we just like put stress on this arbitrary material in like the one direction. Okay, so we'll run I'll say mock experiment. It's like I have a comment. Making fun of my pronunciation. Thanks for that, Cuddy. We'll run a mock experiment by loading material in the one direction. Oh dang! I forgot to put one direction on my lobby songs again. So here we have applied stress. We'll say sigma 1 equals just some generic variable sigma. Okay, and then all other stresses in this matrix equal to 0. So if you thought about that up here in this particular vector, you would just have like this sigma 1 entry as sigma. That's kind of what we're doing here. We're just giving like sort of a uniaxial tension here. Okay, so if you did that, you could do this matrix math where you'd have like epsilon 1 is S11 times sigma 1, right? And continuing with your matrix math, epsilon 2 would be S12 times sigma 1, so on and so forth. You know, you do your traditional matrix math all along the way, and you could determine what the strains are then in terms of like the stresses that you apply. Where here we're applying the sigma 1. So in this situation, then the strains would look something like this. Again, this is a 6x1, where we have like S11 times sigma, or what you might call sigma 1. Let's just remind ourselves that it's in the one direction. And then 0 is kind of in the bottom here. All right. So this would be the resulting strains in this situation. And having these strains in terms of like the uniaxial stress that applied, we can now like think about what the material constants would pop out looking like. Okay. And so if we then looked at this general idea here and we wanted to define, let's say, the modulus in the one direction, well, sort of by definition, sort of what we know as the modulus in the one direction is just the stress divided by the strain in the one direction. So this is like sigma 1 over epsilon 1. All right. Well, if we plug in like this epsilon 1 that we just executed, just sort of up here, then you would see that sigma 1, or that epsilon 1 is just sigma 1 divided by this epsilon 1 entry, which is S11 times sigma 1. We'd have these sigma 1s cancel, and you'd see that the modulus in the one direction is just 1 divided by the S11 entry of this matrix. Or if you wanted to flippy floppy, you could write that the S11 entry is just 1 on the elastic modulus in the one direction. So this is how you might go about building the S11 entry of the compliance matrix if you had the stiffness in the one direction. So this would be one entry that you need in the S11 or in the compliance matrix S to get your compliance matrix going. This written here in terms of the modulus in the one direction. Okay, you can do a similar thing for Poisson's ratio. Where we know by definition that, like, let's say the Poisson's ratio 1, 2 is equal to the longitudinal divided by the transverse strain. Actually, the other way around. So it's the transverse strain divided by the longitudinal strain. This is the definition of your Poisson's ratio. All right, so here we could again write these in terms of like this uniaxial stress in the one direction that we provided above. And so we want to look like at the module or the strain in the 2, the strain in the 1. And so we have the strain in the 1 here, the strain in the 2 here, both in terms of the applied uniaxial stress sigma 1. And here we would have something like negative, we got to retain the negative, S12 on sigma 1 divided by epsilon 1, which is S11 on sigma 1. All right, these guys are going to cancel. You'll end up with a Poisson's ratio. Nu 1, 2 is negative S12 over S11. But we know from up here that S11 is just 1 on E1. So I want to take this then and plug it in down here. And you can do that. And you would see something like Nu 1, 2 is equal to negative S12 times E1. Okay, because the S11 here is on the denominator. And the idea then is that you could solve this for S12, which is the entry of the compliance matrix that you might want to write in terms of engineering constants that you know. And the idea here is that you could write S12, another entry of the compliance matrix, as negative Poisson's ratio 1, 2 over E1. So this is a entry in our compliance matrix in terms of the Poisson's ratio and the elastic modulus in the one direction that you might measure by, like, you know, a uniaxial tension experiment, like the kind of the mock experiment that we're working on. Right. So we did the Poisson's ratio in 1, 2. You could also do Poisson's ratio 1, 3. It's the same idea. You'd have negative epsilon 3 over epsilon 1. You could work this down in the same way and determine that the S13 entry is simply going to be negative Poisson's ratio 1, 3, which again you might measure by experiment, divided by E1. Clean this up a little bit. Okay, so this is kind of all the information that we can garner from this mock uniaxial tension test in the one direction. Okay, so the point here is that with this mock experiment, in sigma 1 can get your S11, S12, and S13 entries. U1 and nu 1, 2 and nu 1, 3, which you might measure in a more traditional manner by experiment. Right? Okay. Now that is only doing a mock experiment in the one direction. Okay. You could do these mock experiments in every direction. All right. You could do the mock experiment in the 2 direction, the mock experiment in the 3 direction. You could do a mock shear experiment, you know, in the 1, 2 direction, 1, 3, 2, 3, etc. And you could go through the same procedure for all sort of these 6 like mock experiments that you could come up with. Okay, so I'll say could also do mock experiments in, I'll say, the 2 through 6 directions. That's not technically accurate since we don't have 6 directions, but hopefully you understand what I mean, right? Like you could do something like sigma 2 only, sigma 3 only, sigma 4 only, which remember we call as like tau 2, 3. You could have sigma 5 only, which is like applying only a tau 1, 3, or you could have sigma 6 only, which is applying only like a tau 1, 2. So you could perform mock experiments with all 6 of these like configurations or ideas. And so we could continue down that pathway and come up with the following information. If you did this mock sigma 2 and sigma 3, all right, I'll scroll up a little bit if you're still sort of copying this down. For this like Mach 2 and 3, you would end up with the following. Okay. These are like 3 more entries to the compliance matrix that you might see. So this sort of the Mach in the 2-dimension direction. If you did the Mach experiment in the 3 direction, you'd see the following. 3, 1 is something like this. And finally, okay. So these are writing all the entries of the compliance matrix in terms of engineering constants. I think we're more comfortable talking about engineering constants because we can sort of physically interpret what the modulus in the 3 direction is, or Poisson's ratio 1-2 is, right? Like, what is my relationship between the elongation and the 2 versus elongation of the 1? I can like physically understand and interpret what that actually is. So for me, that's more comfortable understanding that. Right. For these experiments, reminder, you're in pure shear. So this would be like a torsion experiment. If you sort of wanted to actually do the experiment, you would put this in pure shear, which would be a torsion, a torque on the piece. If you were putting the torque sort of in the 2-3 direction, you would have something that looked like gamma 4 is equal to S4 sigma 4. Or what might pop out of this is that S4 is 1 on G23. Similar idea. You'd have that S55 is 1 on G13. And finally, if you had a pure torsion experiment in sort of the 1-2 plane, giving you shear in the 1-2 direction, you'd have S66. Its compliance matrix entry is 1 on G12. Okay. Give you a second with that. It's kind of warm up in my house. Ah, much better. All right, so what's the point? Well, after doing all these mock experiments, you could then write for yourself what looks like the full compliance matrix in terms of engineering constants that you might get by experiment. Okay, so all together. Here we can write the compliance matrix S in terms of engineering constants as the following. Oh God. That's not it. Here. I'll give you a second with that one. Okay. So maybe you're still copying this down. It is in the notes if you want to just sort of take that to heart. I'm just going to make a couple more comments about this particular guy. This particular compliance matrix is specific for an orthotropic material. Okay, for orthotropic material. And this was an assumption that we sort of made at the beginning of sort of the derivation of this guy. And remember, an orthotropic material, it requires 9 independent elastic constants for us to write this orthotropic material. Okay, and if we actually take a look at the compliance matrix that we have here, we do have 9 independent entries, but here now they're not like S11, S12, S13, S22, S33, right? It's none of that anymore. They're actually engineering constants, and there are 9 of them here. So now, shown as things like E1, E2, E3, new 1, 2, new 1, 3, new 2, 3, G1, 2, G1, 3, and G2, 3. Okay, these are our 9 independent entries of the compliance matrix that we require to fully define behavior of an orthotropic material. So they're shown in terms of this like engineering constants instead of S11, S12, dot, 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 dot. Okay? So those S11, S12, S23, blah, blah, it doesn't really make a lot of physical sense to me. These engineering constants, I understand. Okay, I can physically sort of wrap my mind around what these are. And so if I do an experiment and I calculate what all of these are, I can take information from that experiment and populate the compliance matrix here so that I can sort of carry out my Hooke's law calculations that I might be more proficient with computationally. So it's a lot easier to work with like this matrix here if you're doing computations, right? If I know the stress state at a certain point and I want to know the strain state, okay, well, I need a transformation matrix to get me there through Hooke's law, and that might be this 6x6. And so when I'm working in MATLAB, this is going to be advantageous to have this. But when I'm just talking about material response and material behavior, and I want to talk about like, okay, what is the stiffness in the one direction, which is like a physical property I can really understand, then I probably want to talk in terms of like E1, E2, and E3. I don't want to talk about, oh, the stiffness of this guy is the inverse of the S11 entry. Like, okay, great. The inverse of the S11 entry on this particular material is so high. You know, it's like, no one talks like that. They say the stiffness in the one direction is very high, right? So depending on sort of what you're doing with your particular problem or your particular calculation or discussion, maybe you want to use the 6x6 and populate it with these values accordingly, or maybe you just want to talk in terms of these independent constants, which is just generally more comfortable when you're talking about a physical, tangible property of these materials. All right. So if you're attacking a problem, you probably want to keep in mind that the inverse of this compliance matrix is the stiffness matrix, right? So just remember that mathematically speaking, C is the inverse of S, and vice versa. Okay. And for those of you that have taken linear algebra, you know that trying to calculate the inverse of a matrix is messy. Let's just say that. If you want to calculate the inverse of any matrix by hand, you've got a lot of tools in your tool bag. Words like the Jacobian, the determinant, those sorts of things probably come to mind when you're thinking about taking the inverse of a particular matrix. And in this situation, I'll say that if you wanted to write the stiffness matrix C in terms of like engineering constants E1, E2, and E3, it would be a nightmare. It would be a complete mess. You don't want to do it, trust me. So I'll just say writing the stiffness matrix C in terms of engineering constants for an orthotropic material is a nightmare. I'll just say it's a mess. It's like my room. So more commonly, people populate the stiffness or the compliance matrix S, then use this inverse relationship that C is the inverse of S. Right. So that's how it's done in the real world. Okay. Like if you asked me to create a stiffness matrix for some material over there, I'd go to the lab, I'd find the engineering properties for that particular material, plug them into the compliance matrix S, which you see above there, invert that particular matrix, and hand you your stiffness matrix all pretty. Okay? That's how the pros do it. All right. Now, what about your materials that have higher level of symmetry? All right. So here we've generally talked about orthotropic material, and remember that an orthotropic material has 3 orthogonal planes of symmetry and requires 9 constants to fully define. So what about reductions to like transversely isotropic and isotropic conditions? Right. All right. So what about further reductions if we know more about planes of symmetry? Well, we can sort of go back to our initial mathematical rotations and talk about if we have a transversely isotropic material, what do we know about certain entries of the compliance matrix or certain entries of the stiffness matrix? Well, we talked about this before, but for transversely isotropic materials, we need 5 independent constants. And through our sort of symmetry of relationships, we know the following to be true. That is that the 1, 2 entry of S of the compliance matrix is equal to the 1, 3 entry. And that's because the 2, 3 plane is a plane of isotropy. Right? The 2, 2 entry is the 3, 3 entry. And that's again because everything sort of in the 2 direction is the same as things in the 3 direction. Because the 2, 3 plane is a plane of isotropy. Continuing. S55 is S66. This is related to G12 and G13 being the same. And then we had one last little sneaky one here that we obtained through mathematics, which I'm not going to ask you to prove this, but this S44 entry is 2 times S22 minus S23. This is purely kind of from the mathematical relationships of transforming planes of isotropy, which is a little bit kind of complicated. But this leads to, okay, the following. If you looked at like this particular relationship, okay, we know that S22 is 1 on E2. If we'll just do this one as an example. Which obviously leads to E2 equals E3. I think that's pretty simple and straightforward to see. And we can derive some other pieces of information from these other relationships. And that would be like the following. So E2 is equal to E3. I think that one's pretty obvious to understand. If the 2-3 plane is the plane of isotropy, then the modulus in the 2 direction is the modulus in the 3 direction. Also the following. Nu 1, 2 is nu 1, 3. We have G12 is equal to G13. So this is the shear modulus that defines the relationship between the 1 and the 2 directions and the 1 and the 3 directions. And we also have the following relationship, which looks a lot like an isotropic relationship you may have seen before. That the shear modulus in the 2-3 direction is the elastic modulus in 2 divided by 2 times 1 plus nu 2, 3. And this has flavors of the isotropic relationship. That generally the shear modulus is equal to the elastic modulus E divided by 2 times 1 plus nu. That's terrible. So you've probably seen that relationship before, like in your 3005 class. And that comes from a mathematical transformation relationship that just generally exists between these planes of symmetry. So these guys here are specific for transversely isotropic materials. Okay. And I'll just do the isotropic materials quickly here. So cap it off here. For isotropic materials, a lot of these relationships are pretty intuitive. S11 is S22 is S23. This leads to the idea that E1 is E2 is E3, which is just the elastic modulus E, we typically call it. We have S12, which is S13, which is S23. This leads to a relationship of like nu 12 is nu 13 is nu 23, which we just call the Poisson's ratio nu for this material. And then finally, we have something like S44 equals S55 equals S66, which leads us to G12 is G13 is G23, which we generally call capital G. And these are not independent, and we know that the shear modulus G is actually the elastic modulus E divided by 2 times 1 plus nu. Okay. Okay. So we'll stop it here today. Thanks for coming. I'll see you guys tomorrow, and we'll pick this up right where we left off tomorrow.